really prepare. Okay, because I don't even, why don't you go, I don't even have the title of the talk, so why don't you go ahead? I'm sorry, I'm just
Sure.
meeting.
Okay.
There it is.
Yeah. Today we are very happy to have Gauthier Durieux at the postdoc at CERN. He will talk about a massive amplitude project of standard model differential theory. And this is a very interesting topic. Yeah, you can go on.
Thank you very much for your kind invitation. So I'm indeed going to take this on-shell approach to the effective field theory of the standard model, or SMEFT for short. And this is based on 3 papers in collaboration with Teppei Kitara, who is now junior faculty at Nagoya University, Yael Shadmi from the Technion, Yaniv Weiss, student, and Camila Machado, who was a postdoc in Mainz, and just started now another postdoc at DAISY in Germany. So in basically one sentence, the motivation for taking on-shell amplitude approach to anything is that basically nobody has ever observed Lagrangian. And so it's not surprising that dealing with fields, operators, Lagrangian, which are basically unphysical objects, can be somewhat inconvenient. We have field redefinition redundancy. We can describe the same physics with different fields, and also in effective field theories, relate different operators using field redefinitions. And also, we have a lot of gauge redundancies, which are also somewhat cumbersome to be dealing with. So why not using just particles and constructing directly physical and gauge invariant object like S-matrix elements? And this is a very old idea, which was successfully applied to gauge and QCD in particular, and gravity theories in the past 30 years. And one of the most famous example is maybe this endpoint gluon amplitude, which has this very simple form when expressed on shell in terms of spinor elicity. Elicited spinors. More recent developments are maybe the elegant descriptions of massive particles put forward then by Akani Ahmed, Wang, and Wang, as well as studies of effective field theories in these on-shell formalism. And this is not surprising because effective field theories and on-shell approaches have some kind of communality in spirit, in the sense that the bottom-up construction of effective field theories start from 2 fundamental ingredients, which are the particle content and a set of symmetries. And then what you do is to basically list all terms consistent with those 2 ingredients and construct all operators. And what you obtain, according to Weinberg, is the most general possible S-matrix consistent with those 2 ingredients. So why not going directly to construct those on-shell S-matrix elements? And doing so by this kind of bootstrapping procedure that relies on very simple, even more simple ingredients, which are just Poincaré symmetry, locality, and unitarity. And this on-shell approach to effective field theory has been used quite a bit already in the literature to construct and also classify effective field theories, starting from the soft properties to examine the standard model effective field theory and find and explain non-renormalizations between different operators, non-interferences between certain operators and standard model amplitudes in a high energy limit, or also compute running and mixing at high loop levels or for high dimensional operator, for instance, dimension 8 operator, instead of just dimension 6 operators. You can also literally substitute amplitudes for operators and list amplitudes and then construct bases of amplitudes instead of constructing bases of operators. And this is also something that has been explored and is somewhat efficient. because you don't have to deal with those field definition redundancies and so on. And all those applications so far exploited just the massless helicity spinor formalism. There are also application of the massive spinor formalism to construct, for instance, standard model amplitudes from just the bottom up, or to construct standard model effective field theory amplitudes. And that's where our work is, and that's basically what I'm going to describe to you today.
Before going on, can I ask?
Sure.
I think can I go back to
Yeah.
for this operator enumeration?
Yes.
They completely enumerate all the possible dimension 8 operator, as if I remember correctly.
Yes, that's actually a reference I didn't list here.
Yeah, but what about this dimension 10? Did have upon is also lead to very simplified version, or I mean, dimension 10, dimension 12. Have people think about that?
I mean, people went up to dimension 9 only, I think.
Okay.
But in principle, the ingredients are the same. The principles are the same. It's just getting a bit more messy at higher and higher dimensions. I don't think people have done that explicitly for dimension 10.
Okay.
Yet. And then maybe you can wonder about the phenomenological relevance of going so high.
Yeah.
While we only basically measuring dimension 6 and a few dimension 8 operators so far.
Yeah, that's true.
So one slight annoyance with the construction of on-shell amplitude directly in the broken phase with massive particles is that you don't see at first the relations that are due to the electroweak symmetry and its breaking. So we have to work a bit more to recover those. But the solution is known, and already from the 70s, you only have to impose perturbative unitarity up to a scale lambda much bigger than the masses of the particle involved. And doing so, you actually recover, as phrased in this abstract, Yang-Mills structure when you deal with vector bosons. And in simple cases, you also directly see that you have a Higgs mechanism manifesting itself when you impose such perturbative unitarity restrictions. So this brings me to the program of what we have achieved so far, and also what I'm going to describe in this talk. So first, we bootstrapped effective field theory amplitudes in this electroweak sector of the standard model effective field theory, because the QCD sector is already well studied. We also worked out a full example of 4-point amplitude, which is this Fermi-Fermi Z Higgs amplitude, relevant for Higgs production in decay at colliders. We observe, as I just explained, the emergence of the electroweak symmetry from perturbative unitarity. We established a correspondence between the amplitude and the operator coefficient. It's kind of a matching, a dictionary between those two ways of computing and actually the same quantities. And finally, in the two latest papers, we also attempted and in some cases achieved systematic construction of massive contact terms. And that's also something I want to describe. But first, let me tell you a bit or remind you a bit about the massless and massive spinor formalism before we can go on with that program. So the massless spinor formalism, the representation of massless particle is basically by now textbook material, and you find very nice reviews here in case you're not very familiar with that. It's useful to look at the little group transformation, which is a set of Lorentz transformation leaving a momentum, given momentum invariant. And for a massless momentum, this is basically a set of rotations around the momentum axis. So basically U1 transformations. And we know that particles labeled by momenta and also internal degrees of freedom, like helicities, should pick up a phase proportional to the helicity upon those rotations. On the other hand, we can examine those 2x2 matrices constructed from the dot product of momentum with Pauli matrices, and see that the determinant of such 2x2 matrices is just p squared, which must be equal to 0 for a massless particle, which means that this 2x2 matrix is actually only of rank 1, and that it can be written as the outer product of two vectors, lambda and lambda tilde, which I can also represent conveniently as just an angle and a square spinor. But it's just the composition of my momentum, basically in terms of two spinors, is not unique. I can rescale the square spinor and the angle spinor by inverse constants and see that this constant should actually be a phase. And this rephasing that leaves the momentum invariant is actually just this little group transformation. And so what we have achieved here is to find those angle and square brackets, which are a good representation of massless particle because they satisfy trivially the equation of motion for those and also have the correct little group transformations. They only represent spin or helicity 1/2 particles, but because helicity is additive, you can just take two spinors to represent a spin 1 and 3 for spin 3/2 and so on. With those massless particle representation, you can also go and construct massless amplitudes on shell. And those should also transform covariantly under the little group transformation of each of the momenta, which means they should pick up a phase proportional to the helicities of each of those particles. And these little group covariants in 3-point amplitudes, together with the somewhat degenerate kinematics, actually is sufficient to fully specify massless 3-point amplitudes up to a coupling constant. So if you give me the three helicities of the three particles, I can give you through this formula the spinor structures relevant for instance, Fermi-Fermi scalar, vector-vector scalar, and so on, different amplitudes.
Okay, sorry.
Yes.
What do you mean by degenerate kinematics?
It means, for instance, that there is no Mandelstam invariant in a 3-point amplitude. They're all constants, and in the massless case, actually vanishing.
You mean in the real momenta?
I mean, in this case, we can only, for the 3-point massless case, we can only write those amplitudes with actually complex momenta.
Yeah, but if I remember correctly, this on shell 3-particle massive amplitude is from momentum conservation, but I'm not sure this degenerate kinematics would mean, because you impose momentum conservation, you can 3-particle momentum conservation, you can derive the only solution to the momentum conservation, and a little group covariant will fix the 3-point amplitude. But I'm not sure what I mean by degenerate kinematics.
I mean, it's the fact that the kind of kinematic invariant that you have is very limited, is inexistent. You don't have any of those Mandelstam invariants. So it's much more simple than 4-point amplitude. So if you go to 4-point amplitude now, you have a lot more freedom, and you don't have this unique characterization of the amplitude.
Okay,
but,
okay.
I mean, yeah. It's exactly what you said. It's all the ingredients that go into that. This phrase is maybe kind of
okay, got it. I think yeah. In that sense, yes, because okay, sure, got it. Okay, thank you.
Okay, so let me now go to the massive case. So again, we can look at this 2x2 matrix. Its determinant is again p squared, but now it's not vanishing. It's m squared, which means that the 2x2 matrix is of a full rank, of rank 2. Which means I can decompose it into 2 rank 1 matrices, which basically amounts to decomposing my massive momentum into 2 massless momenta. And I can introduce a compact notation for this sum, introducing this new index j running from 1 to 2. 1 is for k and 2 is for q. And then also look at the little group for this massive momentum. And now I can go to the rest frame of my massive momentum and perform a 3-dimensional rotation, which would leave it invariant. So that's my massive little group, which would actually rotate those 2 vectors in 3 dimensions. And so this little group, this SU2 transformation, is actually acting on this new index j, this little group index, and mixing those 2 vectors. So what I found is, again, a nice representation of my massive spin 1/2 particle in terms of those spinors, those massive spinors that satisfy the equation of motion and have the correct little group transformation properties. If I want to go to higher spin, to spin 1, for instance, I can just take 2 of those spinors and take the symmetric combination of those kind of fundamental spin 1/2 spinors to obtain a spin 1 representation, and so on and so forth. For higher spins, I need 2s spinors symmetrized to represent a particle of spin s. And because this symmetrization is actually unambiguous, I can also just drop all those little group indices I, j, k, j prime, and so on, and just bold the spinors to distinguish them from the massless case. And here are a few examples for 2 Fermi and a scalar, 2 vector and a scalar, 2 Fermi and a vector, and so on. So now you also see that there's more than one single possibility for each amplitude. And you can actually count the number of independent 3-point massive amplitude just by using angular momentum conservation. And that number is equal to the number of irreducible representation in the addition of the 3 spins. And we'll see some examples later. So I've discussed massless spinors and massive spinors, but we can also try to go from one to the other by taking a massless or a high energy limit. And for this, it's useful to to exploit the little group freedom that we have and fix the direction of the k and q massless momenta in the direction n of the original massive momentum. And doing so implicitly, one fixes the spin quantization axis to be along this direction n. And if it's the direction of the initial momentum, it means that in the massless limit, we recover helicities, which is exactly what we want. We can also see that this k momentum in the high energy limit would scale like the energy, while the q spinor would scale like the mass squared over the energy. So in the massless limits, this q spinor would actually just disappear, and my massive momentum p would actually just reduce to a massless momentum k. So the massless limits is very simple. In this bolded notation, it just amounts to unbolding up to mass corrections, at least in simple cases where the leading term is non-vanishing. There are also cases where, for instance, here, due to momentum conservation, the leading term would vanish and one would only remain with terms proportional to masses. So I've only talked so far about 3-point amplitude, but we can also bootstrap higher point amplitudes. And for this, we exploit unitarity, which describes for us or dictates for us the analytic structure of n-point amplitudes. And those objects are bound to only have single poles due to the 3-level particle, one particle exchanges, like this one. And the residue of this n-point amplitude on that pole is constrained to be equal to the product of 2 lower point massive amplitudes. On-shell amplitudes. So we can also try to kind of reverse engineer this factorization property to construct 3-level amplitudes. We can just take lower point amplitudes, glue them together, add the correct denominator to reproduce the correct pole structure, sum of all the channels, and doing so, we reproduce the full analytic structure of this full non-trivial analytic structure of 3-level n-point amplitudes. And what we're missing when we do that is only contact terms, only terms which do not have any poles. So clearly, in effective field theories, especially when for higher and higher points, there is more and more contact terms you have to introduce. Listing and constructing bases for those contact terms is the more challenging part compared to just gluing things together here. So we have attempted this systematic construction of contact terms, first in a massless case, in this paper with Camille Machado. The ingredient here are little group constraints, momentum conservation, and this so-called Scouten identity. And we've come up with some algorithmic procedure to do that. Along the way, we've also found a nice relation, a nice identity, which give us the minimal dimension of operators contributing to any helicity amplitudes. And eventually, we were able to list all structures that arise in the standard model effective field theory up to dimension 8. And also in the special effective field theory that includes standard model fields and gravitons, the so-called GR SMEFT. And this is what you can see in these big tables is the list of all those possible operators, or first amplitude, and then you can map them to operators arising in this effective field theory. The massive case, sorry, is much more complicated, and I'll describe it at the end. We achieved a systematic procedure for the construction of 3-point amplitude of any spins, and also worked out explicitly the construction of 4-point amplitudes for spins no higher than 1. And now I'll go to massive 3-point electroweak amplitude, but maybe I can pause again for questions. If no one has a question at this point, let me proceed. Therefore, with this massive effective field theory electroweak amplitudes at the 3-point level. So the assumptions here are, again, this Poincaré symmetry, locality, and unitarity. We assume a simplified electroweak spectrum with just a single pair of fermions and gauge boson and Higgs. Everybody is massive except for the photon, of course. For simplicity, we require a global conservation of the electric charge and the Feynman numbers. And eventually, as I told you, we want to impose perturbative unitarity to recover those electroweak symmetry relations. But can we already say something at the 3-point level where this perturbative unitarity is not really defined? And the answer is yes. We can come up with this rule of thumb, which is that if a 3-point amplitude has a spinor structure that grows like the energy squared, you can put two of those to form together to form a 4-point amplitude, which would also grow like the energy squared. And this, of course, would violate unitarity at the scale of the order of the mass, which you don't want. So one possible way out is first that this 3-point amplitude only arises at the loop level, where the spinor structure would come together with a loop function, which could tame this energy growth. But we here stick to the tree level. And in this case, the only possibility is that those 3-point amplitude only arise at the non-renormalizable level, such that if in this 4-point amplitude, unitarity is only lost at the scale of the order of the cutoff, much higher than the scale of the masses. So let me go first and describe this specific 3-point amplitude, a fairly simple one with 2 fermions and a vector boson, Z. There are 4 terms, which I already listed, and this is again the counting you obtain from angular momentum conservation. One can look at the high energy limit of each of those terms, and the first one has a trivial high energy limit, just unbolding, because each of the 4 spinors here scale like the square root of the energy, like those K spinors I've listed before. We are exactly in the situation I just mentioned of energy squared behavior, which means this amplitude can only arise at the non-renormalizable level and is actually a dipole amplitude. The second one has a non-trivial high energy limit. The leading term vanishes and one remains with only terms proportional to masses. The high energy limits of the 2 last amplitudes can just be obtained from the first two just by parity conjugation, which exchanges square and angle brackets. And calling this amplitude the left-handed coupling and this this amplitude the right-handed coupling, we see that they contribute to the longitudinal amplitude in the high energy limit with an opposite sign and with a factor proportional to the Feynman mass, while the transverse amplitudes come proportional to a vector mass. So this means that the coefficient of the longitudinal amplitude divided by the coefficient of the transverse amplitude in the high energy limit behaves like left-handed coupling minus right-handed coupling times the Feynman mass divided by the vector mass. And this is exactly what you would have expected from the Higgs mechanisms. It's just the Yukawa over gauge coupling. And you also see that you have this pseudo-scalar structure and that this longitudinal coupling vanishes for a vector-like Feynman. So this is exactly what you would expect from spontaneous electroweak symmetry breaking and the Gaussian equivalence theorem. And this is what we wanted to achieve with this perturbative unitarity. And we'll see more of that and maybe make more precise statements when looking at a 4-point amplitude. Another 3-point amplitude.
Sorry,
Sure.
can I go back to the previous slide? No, the one. So the other one.
Yeah.
This one. So, what's the definition of charge conjugated in this language?
I mean, charge conjugation. Let me get rid of this. Charge conjugation here would amount to basically exchange particle 1 and 2, the two Feynmans. So it would be exchanging 1 and 2 labels.
Okay, exchange 1, 2, and probably you're adding some minus sign for the Z boson.
I mean, at the 3-point level, there's no Mandel-Stanley variant.
No, I'm trying to say, as for line level, you do charge conjugation means you usually for the gauge boson, the charge conjugation give you minus sign.
Oh yeah, I'm sorry.
Yeah. Okay, sure.
Oops, it seems I've paused my screen sharing. Let me try to resume that. Okay. So another 3-point amplitude I wanted to discuss explicitly is this 3-vector amplitude, W, W, and Z. You naively expect 8 combinations just by taking either angle or square brackets for each of the pairs of spinors. But you actually see that there is one non-trivial relation between 6 of those products, which brings you down to 7 independent combination, which is again what you expect from angular momentum arguments. Looking at all those 7 combinations and going to the high energy limit, you see that there are linear combinations that grow like the energy squared and linear combination that grows to the that grows like the energy cubed. And those linear combinations should only arise at the non-renormalizable level. In forcing that, you eventually obtain a single renormalizable linear combination, which is kind of non-trivial and involves those 6 different terms here. You can also specialize this result for identical vectors, taking the masses to be equal, and see that there is no fully symmetric combinations in that limit, which means that the triple Z on-shell amplitude vanishes. You also find only fully antisymmetric combinations, which mean that the 3W amplitude must have a coefficient proportional to the fully antisymmetric tensor epsilon ABC, and here we recover the SU2 gauge structure. So we performed this bootstrapping of all 3-point amplitudes and examined the high energy limits. We see that some of those amplitude vanish, like the 3Z amplitude that I just mentioned. We see that some amplitudes only arise at the non-renormalizable level. And we can also perform this instructive exercise in some cases of obtaining a massless amplitude from the massless limit of a massive one. Then one can also establish the correspondence between amplitude coefficients here in blue and operator coefficients in SMEFT in green here, establishing kind of a dictionary between the two languages, which allow us to compute in whatever formalism we prefer and then translate to the other one afterwards. So here I only included dimension 6 operators. So the expansion of my amplitude coefficient stops at order v squared over lambda squared. But there is no other structures for that specific amplitude. There is only 4 different structures. So all high dimensional operators will only contribute to those amplitude coefficients with higher and higher powers of v over lambda squared. So before I go to the 4 points, let me also pose for questions maybe. If there are no questions, let me describe this specific 4-point amplitude with two fermions, Z and Higgs. Again, this should involve contact terms and factorizable terms, and we again perform everything at the non-renormalizable level. So first, the contact terms. You can see that there are 12 of them. It's somewhat non-trivial to see that and see that there is no additional contact terms, but that's the results, those 12 terms. Those coefficient of those 4-point contact terms now, unlike in the 3-point case where the Mandelstam invariants were just constant, here those 4-point amplitude coefficient admits an expansion in those Mandelstam invariants. The leading contribution, there are 4 of them arising at the lambda squared level. They are dipole type contribution, the last and the first one, or vector current contributions. And you can look, it's kind of interesting at the so-called soft Higgs limit, taking the 4 momentum of the Higgs to 0. And in that limit, you can see that all the other contribution actually vanish. And you remain with those 4 terms, which you can recognize to be the 4 fermion Z amplitudes.
Sorry, can I ask a question? Can I ask a question? I probably should have asked it before. It's maybe a little bit of a technical question, but suppose I'm interested in establishing the standard model amplitudes, but for some reason I'm only interested in the longitudinal polarizations. So I just want to know the amplitudes. I want to know the high energy behavior of the amplitudes for the longitudinal polarizations, the one that, you know, naively have the strongest energy growth. If I wanted to establish that with your sort of bootstrap method, would I ever have to look at the transverse polarizations?
Probably not. I mean, the amplitude that would contribute, that would give the leading contribution to the longitudinal amplitude are those which involve for the vector both an angle bracket and a square bracket. So in the high energy limit, if that contribution is non-vanishing, that leading contribution is non-vanishing, then it's basically becoming I mean, it's leading to a scalar amplitude. You have this spinor for nearly 1/2, minus 1/2, and spinor for nearly plus 1/2, which combine into just a vector. And a 4 vector, so a scalar without elicited spinor in the massless limit.
So just to make sure I'm just make sure we're communicating. So for example, if I wrote down all of the you know, the possibilities for these, you know, 3-point functions and so on, just for the longitudinal polarizations, and then I just required them not to violate unitarity.
Yes.
I would get the right high energy behavior. It's possible, for example, that the standard model actually gives you even softer behavior than that. You see what I'm saying? For some amplitudes. But that doesn't happen, or do you know? That's my question.
I don't think it happens. I mean, what we've seen is that yeah, and actually what they've already seen in the 70s, that imposing those unitarity constraints, you find all the constraints you need, all the constraints that
that's right. Those really are all the constraints. If you check the longitudinal polarizations, it seems like.
Yeah, I mean, we've not constructed ourselves all the 4-point amplitude in the effective field theory, but for the standard model itself at the renormalizable level, this was done indeed in the 70s.
Okay, yeah, thanks.
You're welcome. More questions?
Just a quick notation question. This you have 3 numbers between square and the angle brackets. The middle one, the momentum, or?
Yes, exactly. It's a momentum. It's a shortened notation for P1 here, sandwiched between 2 spinors. Anything else? Okay. If not, let me go to the factorizable contributions to this 4-point amplitude. So what we have to do is to take on-shell 3-point amplitudes, glue them together, and sum over all possible channel, as I explained before. Here I'm skipping all the algebra and even some definitions to give you directly the leading high energy behavior of the sum of amplitudes, which is energy growing linearly. And this is for the longitudinal Z case. And the coefficient of those longitudinal amplitudes have this interesting behavior that they factorize into two pieces. The first piece is basically the left-handed coupling of the fermion to the Z minus the right-handed coupling of the fermion to the Z. While the second piece, the second factor, is the gauge coupling times the fermion mass divided by the vector mass minus the Yukawa coupling. So if you see that if you want to, again, ensure perturbative unitarity up to a scale lambda much bigger than the masses, we have two possible choices. Either this first term should vanish up to non-renormalizable corrections, or this second factor should vanish. And in the first case, again, we end up with a vector lag fermion having identical left and right-handed couplings. And the second case is just the Higgs mechanism, where the Yukawa coupling is given by the gauge coupling times the fermion mass divided by the vector mass. So again, and maybe more precisely here, we've seen how we recover those relations due to the electroweak symmetry breaking in the Higgs mechanism by imposing perturbative unitarity.
So can I ask again? Maybe you said this and I just realized I didn't absorb it. What are the principles that fix the non-factorizable contributions?
Here you basically listing everything that is allowed, which means that everything that basically involves the right number of spinors. So you need 2s spinors for each particle of spin s. And then you need to make sure that you cannot write any of the terms you've written in terms of others. And that's what we call a basis and non-redundant set. And I'll go back in more details into that now. So that's the
Sorry, and then once you have a non-redundant set, then it's just unitarity. Or what? What actually fixes them to be the standard model? Or,
I mean,
or the most general
for the
allowed?
For the specific 4-point amplitude, that's what I was writing here. There's actually no constraint arising from unitarity. Those non-factorizable contribution, they all have the expected behavior. They scale like the energy over lambda to some power, which is allowed.
Didn't you have to assume analyticity?
I mean, analyticity, I mean, in this case, it's basically locality, is the fact that you don't have anything in the denominator, that those are indeed local contour terms.
Yeah. So anything that you can write down subject to this redundancy is actually some allowed coupling. And then it's just a question of how much it violates unitarity or not, or right?
Yes,
okay.
Exactly.
Yeah, thank you.
So let me go into exactly this topic, the systematic construction of massive contour terms. And let us start with the 3-point case. So I've already told you that the counting is deriving from angular momentum. It's just the number of irreducible representation in the addition of the 3 spins. And those people here have provided us with a closed form formula for this counting when you order the spins in that way. What we performed in this in our last paper is an explicit construction of all those terms by starting from a massless like ansatz, which is this first line here. So what we started from is similar to the massless case. Each of the spinor products, which is basically either angle or square brackets, raised to the appropriate power, such that indeed you have 2s spinors arising for each particle of spin S. So for this to be a contact term, all the powers should be positive, which means that this ansatz is only possibly applicable for a higher spin bigger or equal to the two smaller spins. Actually, when the in the case of an equality, the ansatz is exactly applicable and simplifies to this expression. In this case, the counting of structures you obtain, if you just do that, actually overshoots the counting you should reproduce. And this is because there are a number of redundancies that arise from spin 1 and higher, which are due to this equality we've already seen in the tree vector case. And kind of remarkably, there is nothing more arising at higher spins. The only redundancies are proportional to this equality. And so you can just remove them and get the right result in that case. In the last case, where the higher spin is bigger than the sum of the two smaller spins, what you can first do is contract the spinors for this higher spin together with the power appropriate, such that you basically remove enough of those spinors to bring you effectively back to this second case where this equality is satisfied, and then the other factor are just the same as the one we've seen before. So we have an explicit way of constructing all those 3-point amplitude for any spin, and now we can go and list them for higher and higher spins, and you can get these long tables, and among ourselves we call that kind of Christmas tree table. And here are the different spin combinations, the number of independent structures, and the number of those redundancies due to this equality I've just shown.
I'll go to previous slide. Sorry.
Yeah.
Previous, this one. I want to understand the notation. For the S1 plus S2 larger than S3, there is 1 to angular bracket plus 1 to square bracket S1 plus S2 minus S3. Does it mean that the total number of 1 to square bracket plus the total number of square bracket equals S1 plus S2 minus S3? Is it convention?
Exactly. So you can take only square brackets, you can take only angle brackets, or say half
mix of them,
square brackets and half angle bracket, and all possible combination. That's what this notation indeed means.
Okay. The second question is about this formula about the counting from angular momentum, rate of gravitation, and spin addition.
Yes.
Why is that the p factor there? How do you, is there any understanding why this p factor should be here?
I mean, this p factor only matters in this case, because otherwise you see that it's just vanishing. And I mean, the understanding I can give you is the one arising from those redundancies. From spin 1 and higher, in this case, you have such kind of equality that arise, and you have to remove the redundancies that it implies. And that's why you have to subtract a certain number of those redundancies. And this exactly counts this number.
Okay. I think I got
it. Go ahead.
Okay, I think I got it. Okay, I think I got it. Because you S1 plus S2 larger than S3, which means you have redundancy. Because the way that you want to angular momentum conservation is you want to does it mean you want to construct S1 and combine to S2, but you get a larger spin at S3 that you want to reduce it.
Yeah, that's a way to see it from angular momentum, indeed, point of view.
Okay, sorry. Okay.
Yeah, that's a nice way to see it. So let me now go to the 4-point case, which is somewhat more complicated and requires some detours. So we can look, for instance, at this 4-point W plus, W minus, W minus contact term, which can kind of naturally be decomposed into two pieces, a piece with only spinor structures and linear combination of spinor structures, and a piece with only Lorentz invariants, like those Mandelstam dot products. So we can think about constructing those contact terms just from combining those two ingredients. Constructing Lorentz invariants and independent Lorentz invariants is a known problem. So if we were able to construct the required spinor structures and list all the independent ones, we could also just obtain contact term from the product of spinor structures and Lorentz invariants. One issue that arises is that when reducing an arbitrary set of spinor structures to a basis, there are relations we exploit that are non-local relations. And of course, when we want to construct local contact term, those relations we don't want to exploit. So we only want to exploit what one can call local redundancies and get kind of a larger set of spinor structure than a basis, strictly speaking. And this larger set we call the stripped contact term basis, because it's exactly the contact term stripped from the Lorentz invariant structure. And once we have that set, what I just described works out. You can just take the product of those two ingredients and obtain what we want. So let me quickly describe a nice way of constructing a spinor structure basis. So this reddish blob here, although it's not related to the contact term, we eventually want to target. But it's nice, so I still want to talk about it. So the counting is of those independent spinor structures is provided from the counting of conformal correlators, and it's equal to that number as seen by these people. So we know that a complete set should involve at least that number of spinor structures. We also want our basis to be to only involve independent structures, and to examine what are independent structures. It's useful to define this P matrix as those people did, and it's constructed from inner product between spinor structures. So what you basically do is take the conjugate of one of them, set the little group indices to be equal, and then sum over those little group indices. And that's kind of the inference between those two spinor structures. And we can construct a matrix from each of those inner products from all the spinor structures in our set. And if the determinant of this matrix vanishes, it means that we have a relation between, at least one relation between those spinor structures, and so they're not independent. So we can exploit that in an explicit construction. And an elegant way of doing so is to pick spinor structures whose leading high energy limits contribute to different helicity amplitudes. Because different helicity amplitudes do not interfere, it means that the P matrix would be diagonal in the massless limit. Exactly because those helicity amplitudes do not interfere. And it means that the determinant of this P matrix would trivially be non-vanishing, because it's just the product of those diagonal elements in this massless limit. And so all those spinor structures that we pick in that way are actually independent. And we see that for each spin, there are 2s plus 1 different helicity assignment, possible helicity assignment. So the number of those different helicity, of those different structures is exactly the number we want for having a complete set. So they are independent and they are complete, and so they form a basis. Now going to massive 4-point contact terms. So that's somewhat more complicated. So again, as I told you before, there are some relations that are non-local, and this arises actually already at the massless level. And relations like this one. So you could think about, because this relation exists, expressing the first spinor structure as the second one in that form. But if you were to do that, you would introduce this denominator with a Lorentz structure. And this is seemingly non-local, although the specific combination is actually local. So that's something that's kind of unwanted. And that's what I was talking about when referring to those non-local relations.
Is that what
in a massive
Nima
case
calls the X factor?
Not exactly. The X factor introduced by Nima is in amplitudes like involving both massive and massless particles. For instance, two massive spin S particle and a photon or a graviton. In that case, you have some residual gauge dependence that you can actually not remove. And this can be understood because it's only a 3-point amplitude, so it should not actually be gauge invariant. And in this case, you introduce those X factor. So going from the massless to the massive case, a new thing you can do is to introduce masses in the denominator, but only in a specific combination when they come together with an angle bracket and a square bracket, because this combination is exactly the polarization vector. So in some cases, you can divide by the mass and obtain a relation for some spinor structure in terms of orders with no non-local prefactor. And this is actually a spinor structure that would have been present in the two Fermi Z and Higgs amplitude, 4-point amplitude that I talked about before. And without removing this one, we would actually have obtained 13 terms instead of the 12 that are required. So all of those massive relations can be obtained from initially massless relation by mass completing them, so to speak. And identifying all the massless relation is somewhat easy. Performing this mass completion is actually not so easy, and that's the difficult part in what we do here. And this makes it also difficult for us to go beyond 4-point amplitude. I mean, in principle, the method works, but in practice, it becomes very complicated to list all those possible relations and make sure to identify the local ones. Also, high spins would be difficult.
Yeah, can I ask a question?
Sure.
So we know if there is a message relation, then your math completed. But is there a way saying that for every, as I say, the independent of message relation is equal to independent of the math complete version? Is there a theorem you can prove it, or is a?
So you're saying that the number of massless relations is equal to the number of massive ones? Is that what you said?
Yeah, I'm trying to say, suppose that let's say I'm starting from the massless particle, right? I'm starting from massless version. I can easily identify all the independent message relation for shorting identity, something like that. But if I'm starting from the massive one, I can easily obtain, not easily, but I can obtain this massive relationship. But is there any one-to-one correspondence?
I mean, there is no one-to-one correspondence between the massless basis and the massive basis. Because, for instance, that term would be present in the massless basis, but is not in the massive case, because we can write in the massive case this relation that doesn't exist in the massless case. So the extent to which the massless results are useful is that we can identify all those kind of non-trivial relations, like the first one here.
Okay.
And then perform the mass completion. But still, we have at this point to examine each of those relations and see whether they allow us to remove something or not.
Okay.
And they allow us to remove something or not when they involve this specific combination, when I can actually take the mass that was here on the left-hand side and divide by it so that I can isolate this term.
Okay, so it's not, in other words, if you're starting from, let's say, it's not easy. Okay, if I understand you want to say incorrectly, is if you're starting from massless space, your IR deformed. It may not, it may have some redundancy, or.
I mean, maybe a way to see it is also that your massless amplitudes by construction preserve the gauge invariance.
Yeah.
There's no masses. This specific combination is actually a combination that breaks gauge invariance. It's basically an isolated polarization vector, which is basically just a mu contracted with some momenta in your amplitudes. So these things are intrinsically breaking your gauge invariance. So they are intrinsically massive features. So
okay, got it. Okay, thank you.
So when we exhaust all the local relations, we obtain this basis of what I call stripped contact terms. And then, as I was describing before, we can just obtain the full contact term by appending positive powers of the Royce invariants to those specific sets of spinor structures. And eventually, there can still be some redundancies that you have to remove because some product of spinor structures times Lorentz invariance prefactor can actually be expressed as local combinations of other spinors and madness time invariants. And this equality is actually exactly the mass completion to that process I mentioned here of this first equality I mentioned before. So if you were wondering what mass completion would be, and this is exactly what it is. So we've performed that procedure with this somewhat tedious mass completion for all amplitudes involving scalars, vectors, and fermions, so spins up to 1. And the results can be tabulated in those long table, which I'll not go into the details. Instead, let me just summarize. So I've tried to convince you that this on-shell approach is powerful because it gets rid of gauge invariance and field redefinitions, which also connect different operators in an effective field theory. We've bootstrapped and studied massive electroweak 3-point amplitudes, worked out a full example of 4-point amplitudes, including factorizable and contact terms. We matched all those amplitudes to the effective field theory of the standard model, and specifically matched the coefficient of the amplitude with the coefficient of the operators, and observed the emergence of electroweak symmetry relations from just imposing the perturbative unitarity. We then looked at the systematic construction of contact term for massive, in a massive case. For 3-point amplitudes, we could provide generic expressions for all spins, while for 4-point amplitudes, we worked out explicitly the result for spins up to 1. And we hope that in the future, this would this program, completing this program, would provide us with new insights and maybe enable new computations. So things one can possibly think about in the future are constructing more of those effective field theory 4-point amplitude. We've just done one explicitly so far. Maybe go in and compute loops, although it remains to say whether it's easier to do in this massive spinor formalism than in the usual Lagrangian formalism. One could think about trying to achieve a recursion relation also for massive amplitudes, or do something called harmonics that was done for enumerating massless amplitude, also maybe port those kind of reasoning to the massive case, although it's also not obvious how that could work out. Maybe one could think about double copying massive amplitude or examining positivity constraints, which maybe have a more simple form or can be derived more easily in this on-shell formalism. With this, I'll end, and thank you for your attention.
Thank you. I'll give you some plot.
Yeah, thanks.
Thank you.
So, any questions? Or if there are any further questions, probably we go to the discussion session.
Do you use computer to do the calculation or do it by hand?
Many things we use computer. I mean, for instance, this mass completion thing. What you basically have to do is to use, for instance, momentum conservation, equation of motion, and so on. So it's always the same ingredients. Scout and identity is always the same ingredients you use in different ways. So you can basically encode those ingredients and then tell the computer which operation to perform. I mean, we don't have a fully algorithmic way of telling the computer, oh, this is actually what you should do to obtain the results. But actually, we can encode all the building blocks and then tell the computer, oh, now perform this, and then perform that, and then guide it through the results in that way. But yeah, this is indeed needed. Otherwise, in some cases, I mean, I've shown simple equalities, but we also have very complicated ones involving, I don't know, 20, 30 terms. So in those cases, it would be very tedious to do that only by hand.